Here we're asked to integrate the function x over the square root of x plus 1 dx. And we're going to do it two ways. We're going to use variations of the u substitution. Method A would probably be the easier way. Method B works. It just takes a little more time. All right, so for method A, the first step is to calculate or to determine what u is. So we choose u in this case to be equal to the radicand x plus 1. And by the way, let me pause it right here. Why are we doing this next step? Why are we taking u equals x plus 1 and isolating the x? We're just subtracting 1 from both sides and we get x equals u minus 1. Well, in this problem, it's going to turn out that it'll be helpful to recognize that that is a definition of x in terms of u. You'll see it when we get down to step 3. We'll refer back to that. Step 2, let's calculate the differential du. We know it's equal to u prime dx. U is x plus 1, so the derivative of u, in other words, u prime is 1, so du is equal to dx. Okay, let's do the original integral, x over the square root of x plus 1 dx. Now we're ready for u substitution. Okay, look at this. A little bit weird. Hold on. First of all, for the differential in the back, we wanted du, but du is simply dx. There's nothing more multiplying it. We have an extra x here that we don't need. So what are we going to do with it in this u substitution? I mean, in the denominator, it's obvious we've got the square root of u, since u is defined to be equal to x plus 1. But what are we going to do with this x on the top? Well, back in step 1, where we established that u is equal to x plus 1, we solved that equation for x to see that x is the same as u minus 1. So just replace the x in the numerator of the integrand with what x is equal to, u minus 1. And now we have the entire integral written in terms of u. The integral of u minus 1 over the square root of u du. And I emphasize that that is because upstairs in step 1, we actually mentioned that x is equal to u minus 1. Now, since it's still a tough integral, we're going to decompose the fraction into two pieces. It's the integral of the first term in the numerator over the denominator minus the second term in the numerator over the common denominator, du. Simplify with the rules of exponents, we get u to the 1/2 minus u to the minus 1/2 du. Take the antiderivative of the first guy, that's u to the 3/2 times the reciprocal of 3/2 in the front, minus u to the 1/2 times the reciprocal of 1/2 in the front, plus the constant c. Replace u with x plus 1, we get 2/3 x plus 1 to the 3/2 minus 2 times x plus 1 to the 1/2 plus c. All right, now let that soak in. You might want to pause before we go to method B. The first step is we choose u different for method B. We choose it to be the entire radical, square root of x plus 1. Okay, now what are we doing here? All right, hold on. Looks like we're doing exactly what we did in step 1 of method A, because we recognize this is going to be a tough problem. Not only do we choose a value for u as the square root of x plus 1, we isolate x in case we have to do a substitution with x. So we squared both sides to get rid of the radicals. That gave us u squared equals x plus 1, and then we isolated x and got it equal to u squared plus 1. We'll be using that in step 3. Step 2, du equals 1/2 x plus 1 to the negative 1/2 dx. Wait a minute, why is that true? By the definition of differential. Du is equal to u prime dx, where u prime is the derivative of u with respect to x. So if I could say it this way, du is equal to du dx times dx. In other words, du is equal to the derivative of u with respect to x times dx. So u was x plus 1 to the 1/2 power, so the derivative was 1/2 times the base x plus 1 to the, subtract 1 from the power, we get negative 1/2 dx. That's the derivative, the differential. Okay, but also, what do you mean also? Well, this problem is going to require that we also know what dx is. You'll see in step 3 why. Also, since x is defined to be equal to u squared minus 1 back in step 1, dx equals u prime du. Wait a minute. dx equals u prime du? Yes, but the u prime is different. This time, it's a derivative of u with respect to u, not with respect to x, but with respect to u. Dx equals the derivative of u with respect to u du. So dx is equal to u prime du. That's dx equals 2 times u du. We'll be using that in step 3. Then the original problem, integral of x over the square root of x squared, or just x plus 1 dx, is equal to the integral of, now do your substitutions. All right, what are we doing here? Let's write it all out and see what's going on. Freeze it. Okay. Well, we had the denominator. That was just u in the denominator, that square root. At the end, we had dx. Well, we knew from step 2 that dx is the same as 2 times u du. So we replaced dx with 2u du. But we still had that pesky little x in the numerator. Didn't know what to do with it, just like in the method A portion. But we had said in step 1 that x is equal to u squared minus 1. So replace x with an expression in terms of u. That would be u squared minus 1. Okay, now we can bust apart this integral. Oh, wait a minute, not necessary. The u's cancel. So we bring the 2 out in front, the integral of u squared minus 1 du. The antiderivative of u squared is 1/3 u to the third. The antiderivative of 1 is u. And then the constants added at the end. So we have 2/3 u cubed minus 2u plus c when we distribute by multiplication by 2. Now replace u with the x's. We get 2/3 x plus 1 to the 3/2 minus 2 times x plus 1 to the 1/2 plus c. Okay, now check these two solutions, method A and method B. Same answer. But in my opinion, method A seemed a little bit easier. But you can do it either way.